a mass of 1 kilogram of water is brought to its boiling point of 100 degrees centigrade using an electric heater of power 1.6 times 10 to the 3 watts. A molar mass of water is 18 grams per mole. So that's 0.018 kilograms per mole. And I put to kilograms because that's the SI unit. We want to get everything as kilograms. Estimate the average speed of water molecules. Assume the vapour behaves as an ideal gas. Okay, so if we're looking at an ideal gas, I'm going to go straight to the data booklet for topic 3. And I'm going to look for something to do with energy, speed, temperature, and see what I come up with. And I can see an equation there. There's not many equations, first of all. But I can see an equation that says E equals 3 over 2 kT. T is the temperature of the gas, and the gas we're talking about is the water vapour. So the temperature of the water vapour is 100 degrees centigrade, but we don't ever do equations in centigrade. We turn them into Kelvin. So the temperature is 373 Kelvin. We've got temperature. But this idea of energy is difficult, isn't it? Because what we're going to do is put in a lot of heat energy into the system, and that heat energy will then turn into the kinetic energy of the water vapour molecules. So actually, instead of energy, we can put kinetic energy, which is half mv squared. And we want to find out what V is, so that's good. So the only thing we really need to know are, what's K? Well, that's a constant, and that's 1.38 times 10 to the minus 23. Is it 23? Yep. And M, and that's the mass of one water molecule. Okay, so how do we know what that is? Well, we know that 1 mole of water equals 0.018 kilograms, and in 1 mole of water there are 6.02 times 10 to the 23 molecules, because that's Avogadro's constant, right? So we can work out that the mass of 1 mole of water is equal to 0.018 divided by Avogadro's constant, which is 3 times 10 to the minus 26 kilograms. And that makes about sense. That's about right. So we're going to take this formula here and we're going to put everything into it. So 3 over 2 times 1.38 times 10 to the minus 23 times 373 equals a half times the mass, which is 3 times 10 to the minus 26, times V squared. Pop all those numbers together and work out V, and you will find that V is 717 meters per second, roughly. And of course, that should be given to, that's one significant figure, two significant figures. So that's 720 meters per second. So really that question was about recognising that the equation you used was energy equals 3 over 2 kT. So the amount of energy pumped into a gas is directly proportional to the temperature of the gas. And that energy of the vapour gas is kinetic energy of the molecules. Question 2. In the kinetic model of an ideal gas, which of the following is not assumed? This is basic recall. You should have the assumptions of kinetic model shown in your revision notes. You need to note them down. There's about 6 or 7 points that you should memorise. So this is adding up to basic recall, not difficult at all. Let's go through them. That is one of the assumptions. The kinetic energy, no. We assume that the kinetic energy of the molecule, it rapidly changes direction, it rapidly changes speed. That is true, and that is true. That's for an ideal gas. Yeah, in an ideal gas, potential energy is 0. So the answer here is B. Question 3. A fixed mass of an ideal gas. Okay, ideal gas has constant volume. Okay, so just remind yourself of the ideal gas equation, just as a point there. This is constant. And so is this and this, okay? Because it's a fixed mass. So that means that the number of moles is constant. R is a constant value. It's the gas constant. So what that means is we're looking at P being proportional to T. Two quantities RS of the gas vary, shown by graph below. Now, P is proportional to T. We'd have a graph that looks like this. But T is always in Kelvin. And that is obviously not the graph shown. So let's see what the question says. What quantities do R and S represent? Well, if we show this graph, we change T into degrees Celsius, then what we'll find is this graph here. So R is on the y-axis is pressure, and S is on the x-axis, and it is temperature in degrees Celsius. Answer is B. Question 4. A fixed mass of an ideal gas undergoes isochoric volume or isovolumetric change. This increases the pressure of the gas, which describes the change in internal energy of the gas and direction of transfer of thermal energy. Isochoric means that the volume stays the same. So let's pop in our equation for the ideal gas. And this increases the pressure of the gas. So the pressure increases. And if that stays the same, that stays the same. This is it. That means the temperature increases. If the temperature increases, that means the kinetic energy increases, which means that the internal energy increases. Internal energy increases, so it's A or B. Direction of thermal energy. Well, we know that the gas will increase in temperature, so the thermal energy must be to the gas. Our answer is A. Which of the following is an assumption of the kinetic model of an ideal gas? Here's the kinetic model of an ideal gas coming up again. We've already looked at those assumptions. This highlights the importance of you learning these assumptions. Okay, so not the gas is at high pressure. There are weak force, no. In an ideal gas, no intermolecular forces. And potential energy is equal to 0. Collisions between yes and no. This is not true. The energy of the particles is proportional to the absolute temperature. That is not true. What is true is the kinetic energy of the particles is proportional to absolute temperature. So a little bit of a trick in there for you. C. An ideal gas expands at constant pressure. The graph shows the relationship between pressure and volume for this change. The change in internal energy of the gas during this expansion is 1,800 joules. What is the amount and direction of thermal energy transferred? The energy transferred is equal to the area under a PV graph. So thermal energy transferred is this area here, or the work done. Because remember that work done is equal to energy transferred. And the area under a PV graph is equal to work done. So what's the work done here? Let's do it. We've got 4 times 10 to the 5 times 3 times 10 to the minus 3, which gives us a value of 12 times 10 to the 2, which is 1,200 joules. And then we already have the 1,800 joules. So we've got 3,000 joules. Now, the pressure stays the same, but the volume increases, which means there's energy into the gas. 3,000 joules into the gas. An ideal gas is contained in a thermally insulated cylinder by a freely moving piston. So this piston is going to move that way to compress the gas. The gas is compressed by the piston, and as a result, the temperature of the gas increases. What is the explanation for the temperature rise? The rate of collision between the molecules increases. Well, actually, we know that the collisions between the molecules themselves is irrelevant. Energy is transferred to the molecules by the moving piston. Yep, it is that, but let's just check the other ones. The molecules of the gas are pushed closer together. No, we know that the distance between the molecules is very, very large in comparison to the molecules themselves. And the rate of collision between the molecules and the walls of the cylinder increases. No, that is the explanation for an increase in pressure. So it's not the explanation for an increase in temperature. So the answer is B. Two containers, X and Y, are each filled by an ideal gas with the same temperature. So that means the temperature of X is equal to the temperature of Y. The volume of Y is half the volume of X. So that means the volume of Y is equal to half the volume of X. The number of moles of gas in Y is 3 times the number of moles of gas in X. The pressure of the gas in X is Px, and the pressure of the gas in Py. And Y is Py. So we have a relationship that relates the 4 quantities of the ideal gas equation, Pp equals nRT. And we want to know what the ratio of Px over Py is. So an expression for Px would be nx r Tx over Vx. So let's pop that up here. Nx r Tx over Vx over Py. So our top line of Py comes into the bottom line there. So we've got Ny r Ty all over Vy, which comes up to the top line. And we have that there. So we can cancel out the r's. So Nx Tx Vy over Vx Ny Ty. Now, Ty is equal to Tx, so they can cancel out. Vy is equal to half Vx, so Nx half Vx. And Ny is equal to 3nx, so Vx over 3nx. And suddenly we can start to cancel out other quantities, and we have 1 over 6. So the answer is A, 1/6.
Question 9. Under what conditions of density and pressure is a real gas best described by the equation of state for an ideal gas? Well, this is a nice, easy one. It's low density and low pressure. The answer is A. Just memorise that and we're on our way. Question 10. Define internal energy. And this is one of the definitions I highly recommend you learn because it is worth 2 marks. Okay, so we know that internal energy is defined as the total potential energy and random kinetic energy of the molecules of the substance. And that is the definition of the internal energy for a real gas. An ideal gas is slightly different, and I think this question might go into that in a moment. B1. Well, let's read out what B says. 0.5 mole of an ideal monatomic gas. Okay, so we're looking at an ideal gas, so that means we can use this equation. And we know that N is equal to 0.46 because it's just told us that. It's trapped in a cylinder, so the volume's constant at 21 meters cubed, and it has a pressure of 1.4 pascals. 1. State how the internal energy of an ideal gas differs from that of a real gas. Okay, well, in an ideal gas, let me just write that again. Ideal gas, no intermolecular forces, which means no potential energy. And if you go to this equation up here or definition up here, we're looking at the total potential energy and random kinetic energy of the molecules. Well, if there's no potential energy in an ideal gas, then the internal energy of an ideal gas is just equal to the total random kinetic energy. There's no indication or no sum allowed for the potential energy because there is no potential energy. The intermolecular forces are 0. B2. Determine in Kelvin the temperature of the gas in the cylinder. Okay, as predicted, we're going to use this. We're going to rearrange for temperature, which is PV over NR. P is 1.4 times V, which is 21, divided by N, which is number of moles, times R, which is a gas constant at 8.31, and that gives us 7.7. The first gas law, the ideal gas law, gives your temperature in Kelvin. It's asked for Kelvin, so there's our answer. B3. The kinetic theory of ideal gases is one example of a scientific model. Identify one reason why scientists find such a model useful. Well, it's really useful to have a model of a system because it allows us to predict behaviours. So if we can say, okay, we know that this real gas is not really an ideal gas, but if it is, if we model it on that behaviour, we can predict what the volume will be, or we can predict what the temperature will be. It's the same with the sun and planets. We always model the planets to have a circular orbit around the sun or any star because it makes the maths easier, right? Because circular maths is way easier than the real system elliptical maths. So we like to create models in science so that it makes it easier to predict and make approximations about what's going to happen going forward. Question 11. A fixed mass of an ideal gas in a closed container with a movable piston initially occupies a volume V. The position of the piston is changed so that the mean kinetic energy of the particles in the gas is doubled and the pressure remains constant. What is the volume of the new gas? Okay, we've got two situations. We've got situation 1 and situation 2. Situation 1, we've got, it's an ideal gas, so let's look at the ideal gas equation. Situation we've got, the pressure is equal to P, and the pressure remains constant throughout. So P1 is equal to P, and P2 is equal to P. The volume in V1 is equal to V, and the volume in V2 is equal to, we don't know, we want to find that out. N is a number of moles, and it's a fixed mass. So N1 is equal to N, and N2 is also equal to N. None of the gas escapes, or there's no added extra. R is a gas constant, so again, that will stay constant. And T is the temperature. We'll call the initial temperature T. However, we can see that the kinetic energy doubles, and we know that kinetic energy is directly proportional to temperature. So that means that the temperature doubles, so it's 2 times T1. Let's find an expression for volume using the ideal gas equation. PV equals nRT. Let's rearrange for volume. So V equals nRT over P. And if we're looking at volume 1, then we've got nRT1 over P. And for volume 2, we've got nRT2 over P. And P is the same, so it's fine. But what we can do, instead of putting T2 there, we can put nR2T1 over P, which gives us V2 equals 2V1. So the volume is 2 times the original volume, And our answer is C. Question 12. A closed box of fixed volume 0.15 metres cubed contains 3 moles of an ideal monatomic gas. The temperature of the gas is 290 Kelvin. A. Calculate the pressure of the gas. Well, it's an ideal gas, so we'll use the ideal gas equation. PV equals nRT. P is equal to nRT over V. N is the number of moles. R is the gas constant. T is the temperature in Kelvin. And V is the volume. And if we plug all of these into your calculator, you will get an answer of 48,000 pascals. So 48 kilopascals. Oh, I shouldn't have put that S on the end. Let's get rid of it. Goodbye. Okay, there we are. B. When the gas is supplied with 0.86 kilojoules of energy, its temperature increases by 23 Kelvin. The specific heat capacity of the gas is 3.1 kilojoules per kilogram per Kelvin. Calculate in kilograms the mass of the gas. Right, we want to know what mass is. We know energy is 0.86 times 10 to the 3. We know that the specific heat capacity is 3.1 times 10 to the 3. And we know the temperature increase is 23 Kelvin. So we've got E equals mc delta T. M equals E over C delta T. So we've got up on the top 0.86 times 10 to the 3 divided by 3.1 times 10 to the 3, which is C, times 23, which gives us an answer of 0.012 kilograms. B2. Determine in kilojoules the total energy of the particles of the gas. Well, this is an ideal gas, and if you head to your data booklet, you'll see that the internal energy of an ideal gas is 3 over 2 nRT. N is the number of moles, R is the ideal gas equation, and T is the temperature. So 3 over 2 times 3 times 8.31 times temperature, which this is now the new temperature, which is 290 plus 23, gives us an answer of 12, well, it's two significant figures, 12,000 joules, but of course we want that in kilojoules, so it's 12 kilojoules. C. Explain with reference to the kinetic model of an ideal gas how an increase in temperature of the gas leads to an increase in pressure. And this is 3 marks. I'm going to take longer than necessary to answer this question. The reason is because it's worth 3 marks and it comes up a lot. All right, so I'm going to really go full on this by using my quadrant. Okay, and my first thing to do is to draw a diagram. So when I'm thinking about the kinetic model of an ideal gas and pressure, I'm thinking about little molecules colliding with the walls and bouncing off. That's how pressure is exerted when you have an ideal gas within a container. Okay. The next thing I'm going to do is write down any keywords that come to mind. And those keywords will be collide, we've just mentioned it. What kind of gas is this? It's a monatomic gas. So we're looking at atoms, we want to include that. We obviously want to include the word pressure, temperature. And with temperature, we're looking at kinetic energy, because kinetic energy is proportional to temperature for an ideal gas. So kinetic energy, I think that'll keep us going just now. Right, any sort of phrases or relationships we want to include? Well, we want to include kinetic energy is proportional to temperature. We want to include collisions with the walls, or collides with walls. We also want to include the equation for pressure equals force over area. So we're beginning to see, the origins from the diagram of what this explanation is all about. We've got some keywords to include, and we've got some phrases and relationships that we need to bear in mind as we build out this answer. And we're going to put our answer not in this fourth quadrant, but actually up here. So, explain with reference to the kinetic model of an ideal gas how an increase in temperature of the gas leads to an increase in pressure. Okay. As temperature increases, the kinetic energy of each atom increases proportionally. Brilliant. 2. This increased speed of each atom results in increased momentum and increased change in momentum when atoms collide with the container. We know what happens when we've got an increased change in momentum, don't we? There's an increased force. So this increased force over the same area means a larger pressure. And to justify that, we're going to put pressure equals force over area. Have we included everything in our quadrant? Okay, well, we've talked about atoms colliding with the walls. We've used the word collide. We've used atoms. We've used pressure. We've used temperature. We've used kinetic energy. We've used this relationship here with collisions will, and we've used that. This is perfect. The perfect answer. And let me tell you, this question is repeatedly asked in past papers. It is repeatedly asked in exams. And it's worth 3 marks. How brilliant is that? So go off, learn it, and make sure you understand it.